Right, did you receive my email?
Yes.
So in the email I sent the exam. It should be pretty simple exam, I hope. It's really not a take-home exam, but
So it's due in 2 weeks, right? Next.
it's due in 2 weeks. If you're already stuck, you can again mention it. It's kind of, whatever.
So the final will be like the same format, essentially.
Final will be based on those questions. Very simple format. A lot of the questions are just true or false. You don't even need to justify.
And then a couple small questions.
Yeah, and a few small questions. Maybe one question that is a tiny bit non-trivial is generalize the Young inequality. Aside from that, I think many of those questions you can find solutions to already in my notes or in the homework or the assignments. But try to see if you can actually answer it on your own. So intermediate, so nested interval theorem. So what we have is we have nested sets. I1, a subset of I2, and I3 is a subset of I2, and I4 is a subset of I3, etc. And the assumptions, one assumption is each IN is closed and bounded. Each IN is closed and bounded, and it's a subset of R. So we're talking about not just any intervals, but intervals in R. And what we then do is, if we take the intersection of IN, the result will not be empty. Furthermore, if length of I sub n goes to 0, the intersection is 1 point. So let's try to prove it. So what I can do is I'm going to draw those sets. Okay, so what you have is the initial set is from A1 all the way to A2. Now the set that is nested within it, I'm not sure quite how oriented, but let's actually call it A1, B1. I'm sorry. So the right hand point is B and the left hand point is A. And then I can draw a closed bounded interval within. So that's A2, B2, and the next interval is within the blue one. Maybe in this case it starts with A2, but I'll call it by a new name A3, B3, etc. What do you observe? Look at the endpoints. What happens to the A's?
Either stay the same or get smaller.
The A's, well, look at it. The A's are moving to the right. So the A's are growing. So what we have is A1 less than or equal to A2 less than or equal AN less than or equal, etc. Is there an upper bound to the sequence of A's?
Yeah,
What is that upper bound for sure?
B1.
B1, right? So however you move this interval and shrink it, you can say that the upper bound is B1. Okay? So what does it imply? This means, as we proved last time, that the AN, they converge to A, which equal to the supremum of AN, where I go over all the n. Right? So this converges to A, the supremum. Look at it. I always move to the right, so so the A's are, this is called increasing.
So what is A?
A is the supremum of the of A1, A2, A3, etc.
Which is B1.
No, we don't know that.
Oh,
Look at it. By the picture here, it's clearly not B1.
yeah.
Because the next interval, wherever it's going to be, it's not going to extend farther to the right than B3. So it doesn't have to be B1, it's just going to be some supremum. This B1 is just some upper bound, and here's where here's where it's important that we're in R. If we have least upper bound, if we have an upper bound, we have a least one.
Yeah. No, I just don't understand what AN converges to A mean, because A doesn't have a subscript, so I don't know what that
Well,
means.
A is the supremum. I just said what it is. A is the supremum of the AN. So I just go look at the upper bounds and I choose the least upper bound. Remember we proved it on Monday. We said that any increasing sequence converges to the supremum of that sequence. Okay, so we have this situation, A converges to the supremum. And now we can do the same thing and examine the B's. What happens with the B's? So we have that B1, what's the relationship to B2? So B1 is greater or equal to B2, B2 is greater or equal to B3, etc.
And then the lower bound is A1.
Exactly. And the lower bound is A1. And what's the implication?
That AN converges to B, which equals the
That
non-supremum,
Bn converges to B,
which is equal to the non-supremum, but in whatever.
infimum.
Infimum.
So infimum over all the n of B sub n. You understand what this means? It means that I just look at the right endpoints of all the intervals, and I take the infimum and I get B. Good? So now my question is, what's the relationship between A and B?
Infimum and supremum are equal.
Well, I don't know that they are equal. It could be that they are. But what can I conclude about this relationship? So we have B is the infimum of all the B's, and A is the supremum of the A's.
Supremum is less than or equal to the infimum of B, and the infimum
All right.
of B is more than equal to the
Good.
supremum of A.
Wonderful. So we need to just make sure that this is the case. It does seem that it should be the case. We would say that A should be less than or equal to B. Okay? In essence, you can almost see by the picture what's happening. We have shrinking intervals, and as we shrink, my claim is that we are going to shrink to an interval from A to B. That's going to be the intersection. It's going to be some interval. Let's try to verify that that's the case. So first I need to make sure that I'm not wrong, that A is indeed less than B. So what you can say is that if on the contrary, you can say, A were bigger than B, then And then what happens, right? So if A is bigger than B, then I can draw this in this picture, right? It might be simpler for you. So here is my A, here is that line, here is my B. If it happens that I see something like this, something is going to be wrong.
Can we say let B equal B1 and that contradicts our statement?
Well, we don't know what B equals, so we just say we're claiming, which seems to be clear from the picture, that
Exactly.
A will be smaller than B, right? The B sub n's, they become B, the A sub n's, they become A. It seems, how is this going to go beyond B?
Exactly. I
Right?
was just saying, can we prove it by saying let B equal B1, let the infimum of B equal B1, then it's a contradiction?
But we don't know that the infimum of B is, well, we don't know what's the infimum of the B's, right? B1 is the supremum of the B's.
I'm not good at proofs.
B1 is the supremum of the Bn, right? You can look at it, it's the biggest guy. A1 is the infimum of the A's. But, okay, what do we have here? So B is smaller than A. But what do we know about A? It's the supremum of An. So what must be the case? So starting from all the terms, we should have An is somewhere here eventually. Correct? Because the An, they go from below towards A. Look at it. Supremum, right? So the Ans, they are encroaching, they're crawling towards A from below. Yep? An are here. And what do the B's do? The B's, they encroach from the right. So you would have the situation that An is here and Bn is here for some interval. And that's impossible. If you want to spell it out exactly, just so what we know is here is the argument. I'm just lazy. So since An goes to A, there exists N1 such that N bigger than N1 implies N bigger than N1 implies that that the distance, the absolute value of A minus An is less than A minus B divided by 2. If you want to, you can divide it by less. Okay? Just again, even to give it room, let's say divided by 4. So if I assume that A is bigger than B as in this picture, then A minus B over 4 is my epsilon. And eventually, if N is bigger than an N, this is going to be the case. This is for all N. Yeah, for all N. Yeah. Okay? So what happens then? And also, Bn goes to B. So there exists N2 such that N bigger than or equal to N sub 2 implies such that for all N bigger than N2, that implies that that B minus Bn is less than A minus B over 4. So just take N bigger than the maximum of N1 and 2. Which implies this picture. Okay? So you see what I'm saying. So An is within a quarter of the full distance to A, and Bn is within a quarter of the full distance to B. So they must be as I drew in the picture. Yes?
can you just say like, right, assume that it's true, right, that the intersection is 0, goes to 0, right? Then Bn minus An.
The intersection, just a second, what do you mean about the intersection?
Suppose the intersection, the limit is 0, right?
Which
the intersection of all the intervals. The limit is 0.
We don't know that. That's further.
No, I'm saying like, would it work if you say, suppose that's true, then Bi minus Ai, then the infimum of B minus the supremum of A has to equal 0, and therefore they're equal.
But we don't know. So you are right. That's furthermore. But you're talking about this extra condition which I'm not using.
Yeah.
Right now I close this condition and I'm claiming that the intersection of the closed intervals is just not empty. If I add this condition, then what you're saying is true.
Yeah.
Okay. But in general, A will not be equal to B. In general, A will be less than B. Strictly less. So there will be a full interval. So you see, those intervals don't have to shrink to 0. If they did, then the A and B will equal. But if they don't shrink to 0, then what you have is a full interval always remaining. Okay, aside from that, you are right. We're going to mention it in a moment. So here, what I just mentioned is what is drawn in this picture, that we have that A is less than or equal to B. So what follows? Hence, the interval AB is going to be a subset of any interval AN, BN, which is IN. Which implies that A, B, the full interval, is a subset of the full intersection. You're seeing the picture, guys? Right? You can make it rigorous and write what I have here, but what's the main idea? The main idea is just this picture. So you have those shrinking closed intervals. And what can happen? As they shrink, the intersection is really just going down, down this sequence of intervals. You see it? And what do we get? We clearly are going to get that this intersection is inside. So this interval is inside the intersection. I'm sorry.
But if we proved that A is less than or equal to B, we can also prove that B is less than or equal to A.
No, we cannot.
Why can't you? You can use
Because
the same.
B is the infimum of the BNs and A is the supremum of the ANs. And just look at this picture. Look at this picture. A's are smaller than the B's. Why would they? That's the proof here. Is by contradiction. If I assume that A were bigger than B, that's not going to work, because then I have an interval with Bn as the lower point, and An as the bigger point, and this is in parentheses. I suppose rigorous explanation of why.
So we can't say that it always converges to one point. It converges to a certain interval.
It converges to it. So here I just showed that this interval is a subset, but in fact it must converge to it, because what happens is that if I take An and Bn, the next one is gonna cut closer.
I get it, but we can't prove that it converges to one point.
It does not converge to one point unless the intervals go to 0. If they go to 0, no, it will converge to one point.
Okay,
Other than that, no, it doesn't.
got it.
Well, think about it, right? So if I shrink it, but I shrink it not too much, it's not going to converge to a point. It's going to converge to an interval. So I'm just going to write here, just verify. In fact, the intersection where n equals 1 through infinity of In is exactly the interval from A to B. I'll leave it to you to verify. So now let's adjust and say that the limit is approaching, the length is approaching 0. Now if length in goes to 0, what does it imply? This implies that the distance, I can do this, right? I can say that the absolute value of an minus bn, this distance is, if I take limit as n goes to infinity, this we know is approaching 0. On one hand, this limit is 0. On the other hand, distance is continuous in two variables. We have that this is just a minus b, absolute value of a minus b, and therefore the length of the interval is 0. And maybe it would be easier for you if I write it this way. Limit the length of in, that's equal to limit as n goes to infinity of simply bn minus an, I don't need the absolute value, which is equal to what? Which is equal to b minus a. It's just a difference of limits, keep it simpler. So, which is what? Which is the length of the interval AB. Yep.
So you prove both ways, right? So it's like only if.
If and only if you want to prove that, suppose that that the intersection is 1 point, that it means that the intervals go to 0. That's what you're asking, right?
So is that what you just proved earlier, like right before this? What did you prove right before this?
Well, what I proved right before is without this assumption, without the assumption that the length of the intervals goes to 0, the intersection of all the closed intervals will be not empty. In fact, I proved that it will be a closed interval. Right? So it's going to be some closed interval AB, where A is the limit of the left endpoints and B is the limit of the right endpoints. If it further happens to be that the length goes to 0, then B is equal to A, and this interval is really just 1 point. Okay? So in general, it's just an interval, but in the special case where the intervals shrink, A and B, they merge together, and you just have 1 point. Good? Makes sense? Very easy proof, but definitely geometrically, right? So here is an interval, you shrink it, you shrink it, you shrink it, you shrink it, you get 1 point. Or you get an interval. So let's see examples. So is it necessary to assume that the sets are closed? Is it necessary to assume the sets are bounded? Okay? So let's look at this example. Let I sub n equal to the closed interval from n to infinity. So you agree that this is a closed interval in R. And do you agree that that if I look at I1, it's going to be containing I2, where I2 contains I3, etc. So my question is, what's the intersection? The intersection to infinity as n starts from 1 of the I n. What is it equal to, please?
I want to say infinity.
infinity, so this symbol only means growth without bound. The intersection is what points are in. So you see we have this. So look at the set. Where do we begin? It's 1. The interval is from 1 all the way to the right, to infinity. Next it's 2, all the way to the right. Next is 3, all the way to the right of 3. What's the intersection? 0 is not even contained in any of them because
It's nothing
It has no up
Right.
and down.
because there's no
One
intersection.
point goes to infinity.
if infinity were a point, you will be right, but notice that's why we have this open bracket, right? So
Infinity minus
R does not have this as a number, right? The symbol is not a number in R. So the intersection is, well, or empty set. So the intersection is an empty set. So what's the problem? Well, you see, how could it be empty? Didn't I just say it cannot be empty? What's wrong with this? Oh, it is closed.
It is closed.
It's not bounded. So what's wrong? That's right. What's wrong here?
Get it. This is sexy.
What's wrong? Well, you look at this interval. So if you look at in is just that part of the number line starting from n and going forever to the right. Not bounded.
Isn't the supremum algorithm
The supremum of this thing,
of IN, yeah?
the supremum is going to be infinity. If you do it, you can calculate the supremum in the extended real number system. Okay, so not bounded. You can say that, not bounded because length is length of in is infinite. Let's know is cardinality. It's just really saying that what you have. When you say Aleph null, you have to refer to what? To the points that live in the interval where it's much bigger. The points living in that interval are the size of all the real numbers. The size of the interval from 0 to 1. So it's not Aleph null. What this symbol means is just that the length is not finite. Length is bigger than 5, 7, million, trillion, any number you can think of. This is bigger, the length. You follow me, guys, yes? So another example B. So now what we're going to do, so let the in be equal to,
Wait, can I
Yes?
ask so the maximum IN, right, is less than infinity, right? Because infinity is not included, right?
so the upper bound is not including this thing.
So it's not infinite. So it means you can have on the left-hand side and the right-hand side, there's a number that exists that it goes to, right?
What I mean is what the symbol means is this. So you have a number line. What is the real number line? It's like an infinitely extended ruler, infinitely extended to the left and to the right. So what do? I take this ruler, I find the number n. So first I find the number 1, and I cut that part of the ruler that starts at 1, and I take the right-hand part of it. That's what this means, okay? So you just have a stick, a half open ray, a stick that begins at n and goes on indefinitely. The length is just going on and on and on, no matter how you look at it.
Why is it closed and not open?
It's a closed set. Closed means closed set. Not you see. So maybe you look at this, and this circle bothers you here. This curved bracket bothers you. Take the complement. What's the complement? The complement is an open set in R. The complement is all the numbers smaller than n. It's an open set. So this is a closed thing, and it's an interval. That thing. So it's called a closed interval. In R, it's closed. Okay. You see, you have this structure as well. You have the structure R bar, and this is compactification of R. That's from minus infinity to infinity. And what you mean is that you do consider those objects as endpoints. Okay, so there is this structure, and in this structure you can say that the supremum is equal to infinity. So usually when I say supremum is infinity, I think, well, I calculate the supremum in the complete structure here. Okay? So this is the extended real number system. All right, so in this, let's take another example. Let In equal to something like this. Let In equal to the interval from 0 to 1 over n, and I take it to be open, right? So you can clearly see that we have I1 is just the open interval from 0 to 1, then it's the open interval from 0 to half. So it's nested. You agree it's nested? So now I'm asking what's the intersection? What's going to be the intersection?
It approaches 0, but it can't be.
Right, so you see this wall is, so one wall is at 0 but not including it, and the other right wall is closing, it's moving in, like this. So are we squeezing any number? No, because other than 0, every positive number is eventually to the right of the wall. Right, the wall is going to slide, so let's say, is this point in? No, because eventually the wall moves past it. So the intersection is very clearly, again, empty set.
But it can't be because it's not closed. Everything isn't closed.
So it's an empty set, and what's wrong?
It's not closed.
Yes. So you can say that In is not closed. So you see it's bounded, but it's not closed. So maybe other examples. If I have, if one of the conditions is violated, so the set is not closed or it's not bounded, can I conclude the intersection is empty? Simple question. Right, so I have a bunch of nested intervals. They are not necessarily closed, not necessarily bounded. Can I just conclude the intersection is empty?
No, you can't.
We can't.
Because it can't converge to a set if we wanted to. For example.
Right. Yeah. It's like this, right? Look what this theorem is saying, right? If it rains, I'm wet, let's say, because I'm outside, right? But if I'm wet, does it mean it rains? No. Maybe a dog peed on me. So that's the same thing. So what we have is we can take, for example, let In equal to this type of set. I'm going to make it neither open nor closed, but bounded, let's say. So maybe it's something like this. So it's minus 1 over n, minus 1 over n. Now, yes, minus 1 over n to 1 over n. Something like this. So what is the intersection?
0.
So you see neither open or closed, but bounded in this case, the intersection is 0. Only the point 0 is there. Good. So another thing that I want to make a remark for, that's going to be important soon. So if I1 subset of I2 subset etc. of IN is a nested sequence of closed and bounded intervals of R, and if x sub n is a point in I sub n, then I forgot to mention, assuming that that the length of the I sub n goes to 0, xn converges to the point A, where A is the intersection. You agree? So why is it true? You can think of the nested interval theorem dynamically. You can think of this as two walls. One wall at A, one wall at B, and the walls are closing in, like in Indiana Jones. They're closing in. So A1, B1 is the initial interval. The next one, the walls moved at some speed. The walls moved at some speed if the separation between the walls is closing. So Indiana Jones, there is nowhere for him to run. He just runs between one wall to another, and he will be squished. That's the sequence where he goes, right? He will be squished to the merging point of both walls. Easy. So we have seen what open sets are, closed sets, limit points, all that stuff. And now we are talking about perfect sets. What are perfect sets? So this is the definition. A set P is called perfect if it is empty, or if it is, first condition, it has to be closed, and second condition, every point of P of P is a limit point. Of P. Okay? So what makes the set perfect? Why do we have this name? Well, notice that no point of P is isolated. Right? So everyone that lives in P has friends that are nearby. So simple question, can a perfect set, other than the empty set, could it be finite? Could a perfect set be finite? No, right away not. Could a perfect set be open? Example?
You just said no, you just said closed. The null set.
But does being open contradict to being closed?
You said it's both closed.
Right, so a perfect set has to be closed. And each point has to be a limit point. Okay? So closure means that, well, the fact that it's closed, it means that it doesn't touch points that are not members of the set. Okay? So it's an exclusive club. Everybody in this club has many friends, and nobody outside of this club has friends from this club. That's closed, and that's what perfect means. But could it be an open set? Sure, it could be. Closed and open are not contradictory. So let's look at some examples. So R, or the interval minus infinity to A, and of course, well, you can take this set or the interval A to B, and it's to be closed, are perfect sets. Of R. Do you agree? So here is an example of a set in R that is both closed and open. R is open relative to itself. Okay? So this is a closed set, and every point in that interval is a limit point of that interval. So it's closed.
Is every point in R a limit point?
Yes, it is.
Doesn't the limit point have to have put a circle around it points that are in R?
Well, no. A limit point, so take a point in R, right? So here. Here is R, and then what we do is we are going to extend an interval. So this R is a real number. Is this guy a limit point of other members of R? And the answer is yes, because each interval contains rational numbers. So if you take this, if this set is, you can take this to be R minus epsilon, R plus epsilon. Any open ball around R is of the form R minus epsilon, R plus epsilon. So what must be here? And here must be some number m over n, a rational number. And the rational number is a real number. So this guy is a limit point of rationals.
Yeah, but when did you define that? Like, I mean, so any set that's rationals contained in R, so isn't it still an interior point of R?
Yes, it is. I didn't say it's not. Yes.
So it can be an interior point and a limit point at the same time?
Of course.
Oh.
Interior, because always ask this question, interior point of what? A limit point of what? Okay? So what does it mean for me to be an interior point of a set? So let's say that we have a huge crowd of Arkadys, right? So the set is A. Me, a particular Arkady, is a limit point of Arkadys if what? If I have, if you just draw any circle around me, within that circle stands another Arkady. Somebody whose name is Arkady, correct? What does it mean for me to be the interior point of the set of Arkadies? It means that I can draw a circle where I'm surrounded by bodyguards that are other Arkadies. Yes? Which I need in certain classes, hopefully not in this one. Good? You understand what I mean? So an interior point means that I'm protected by the set. So if I'm an interior point of some set, I'm protected by that set. I have a full neighborhood that defends me. I am a limit point if furthermore it means that right next to me I have bodies. That means that every circle I draw around me, that circle contains another Arkady. Let's say. Make sense? So this real number has real number friends right next to him. So he is a limit point of other members of R and of the real numbers. And he is, of course, an interior point because you can take this full interval, everything it contains is only real numbers. So here I'll write y. So B. So if I take the interval AB, or if I take the interval closed A, closed B, union some point C, where in this case I have, so maybe I'll draw the set. So the set I mean here. So this is A, this is B, and here is C locally. If I take Q, or if I take the irrational numbers, which is all the real numbers that we remove rationals from, are not perfect. Are not perfect subsets of R. Do you agree? What's the problem? Why is this guy not perfect? Yes?
C is in the limit point.
Well, that's here, but if I just look at the first guy, the interval from A to B, open interval. Why is this not a perfect set?
B is a limit point, but it's not on the side.
Exactly, right? Exactly. So this set satisfies a lot of the condition to be perfect. But what's the problem? It's not closed. Okay, every guy you take in this interval is a limit point of other guys of the interval. You agree? But A is a limit point of the interval, it's not part. And B is a limit point of the interval, it's not part. And then you mentioned this set is not perfect. Well, is it closed? Yes, closed. But the problem is what? The problem is a member is lonely. Members are not supposed to be lonely. So C is not a limit point, it's not a perfect set. What's wrong with Q? And notice I said not perfect subset of R. All of those are relative to what space you consider. What's the problem with Q?
Every point is an limit point.
Every point of what is not a limit point of what?
Every point in Q is not a limit point of R.
No, it is, because every point in Q is a limit point of Q.
Is Q not closed because it's not 0?
It does have 0, but is Q closed or not? What's the problem? Why Q is not closed? Countable, but countable doesn't mean there's anything wrong with it. Why is it not closed?
The complement is open, no?
No.
Why is the complement?
The complement of Q is the irrationals. So I'm claiming something is wrong with Q. Why is Q not perfect? Is every point in Q a limit point of Q? The answer is yes. Do you see why? What have we verified using the Archimedean property? If we take two real numbers, no matter how close those two real numbers are placed, in between them there is a rational number. What does it tell you? It tells you that every real number is a limit point of rationals. Do you see that? So always make sure that you can verify this. Can you prove that between any two real numbers there is always a rational? If the answer is that you can prove this, that means that every real number is a limit point. Now Q is just a subset of real numbers. Of course, then every element of Q is a limit point of Q. What's the problem? There are other limit points, right? Q has R minus Q also as its limit set.
So why isn't it closed?
Well, because it does not contain the irrationals. It is very voracious. The rationals are very voracious. They touch, so the rationals are spread around, so they are close nearby to any irrational number, as well as any rational number. They are dense in the real number line. That's what dense means. Everywhere you look, you find rational numbers. They are, basically every real number is a limit point of rationals. Some of those real numbers don't happen to be rationals. Okay?
So how come that doesn't work for the second example you gave? You said that the interval from A to B union C,
Right?
is a closed set.
It is.
But you can say that that Q is just the union of all the integers.
No, it's not. Again, you're glitching. Q is not just the union of the integers.
Excuse me. Excuse me, yeah.
Q is the union of all fractions.
Yeah, yeah. Excuse me.
Right? Good? You see, Q is countable, so maybe that's why you say it's the union of the integers. It's countable, and therefore I can count all the rationals, 1, 2, 3, 4, 5. But the counting is really crazy. Think about it. Take any small interval, there are infinitely many rationals there. Take a smaller interval, there are still infinitely many rationals there, but somehow you can count them. We showed how.
So you said Q is not a perfect set because there's rationals around every element of Q.
That's good, but there are also rationals around every element of not Q. So it's not closed. Okay?
I meant real. I meant there's
Right,
there's numbers around Q.
Right. So you can even immediately stop. As soon as you know a set is not closed, it cannot be perfect. It has to be closed. That's one of the conditions. Okay? They are not perfect subsets of R, not closed. Okay, so with the irrationals, just take root 2. You can do the same argument. By the way, maybe I should have asked this for the exam. Prove that the irrationals are dense. Can you show that between any two real numbers, there must be an irrational number? Just like I can show that with rationals. Can you do that? See, I made a mistake. I should have updated this to your assignment. So that was B. C. So suppose that what we have is a sequence xn, which is a subset of some metric space MD. And we know about the sequence that x sub n converges to x in the metric D. So, first question, is the sequence xn, maybe I can just write it just as a set, the set A, which is xn such that n is bigger than or equal to 1, is it perfect? this perfect?
Okay. Can you clarify when you say xn under d converges to x, you mean any, like xn and xn minus 1, the distance function on that becomes x?
So, as basically when I measure the distance from xn to x, I see that the distance decreases to 0 as I delete the initial terms of the sequence. So I delete x1, x2, x3, I see that the distance shrinks and eventually shrinks to 0. So the sequence, the points of the sequence cluster around the point x. Can I claim that the sequence is perfect, or I cannot do so?
It's closed.
Is the sequence closed?
Yeah.
To be closed, it must eat all the limit points. If I just take the sequence, what is the limit point that the sequence has? X. So to be closed, so first what I do is this. I can take a closure, see if a closure is perfect. I don't even need to say one, right? So that is the question. So if I take a closure, that will be A union X. If it happens to be convergent to one of the elements in the sequence, then this union is not necessary. Okay? So a closure is A union X. I just need to give it possibly one limit point, if X happens to be a limit point. Remember, there is a difference. Sequence might converge, and yet what it converges to might not be a limit point. For example, if the sequence is eventually constant. Okay? But if the sequence is infinite, this X must be a limit point. So we have this. Now, could this possibly be a perfect set? So this set now would be closed. Is it perfect?
Can it possibly contain limit points that aren't limit points?
No, others, it cannot possibly contain other limit points. Think about it.
No, not other limit points. Like, but the first x1 might not be a limit point because it might not have x2 right next to it.
Right, exactly. That's very good. So regardless of the situation, you know it cannot be perfect because, so closed but cannot be perfect. We will return to this point. I will just ask why right now. I will return to this point. You will see maybe simply why that cannot be the case. But you heard the answer to it. Well, one thing is I look at the terms of the sequence. Think of those of X as that sugar cube to which the answer attracted. So the answer clustered around one point. They are not clustered necessarily around. So each ant in a sense is isolated. Either we have finite, either the sequence is finite, in which case there is no way it can be perfect, or if it's infinite, again you will find someone isolated. Okay, that's really going to be why it's not going to be perfect. We'll revisit this topic. In fact, do we have time? We can actually say something about it now. Theorem. If P is a subset of R, P is not the empty set, so the empty set is considered perfect, but if P is not the empty set, and P is perfect, then P is uncountable. Okay? It has to be in R, but you have to be really careful. In R, a perfect set that is not empty is automatically uncountable. How do we know that? Well, we can go by contradiction. Assume B is equal to, let's say, xn, n equal 1 to infinity. In other words, assume it's countable. Assume I can list all the points in P. Consider the following. Consider, let's say, I consider I1 to equal the closed interval from, let's say, x1 to x2. Maybe I should be careful here. So what we can do is we can let x, which we can say is equal to x1, belong to the set P. And then we can consider I1 to be the closed interval x1 minus 1 to x1 minus 1 half, let's say. Minus 1 half to x1 plus 1 half. Okay? So what do we know about so we have that length of I1. I just create an interval, its length is going to be 1. Okay, so what I'm doing is this. It's really a very, very simple proof. It's just a little annoying to write it. So let's say I picked this point x1. Okay, and I created a closed interval. Since the set is perfect, x1 is not lonely. So you know this interval must contain within it other points. So what we have over here, we have some first element. Without loss of generality, the first element that the smallest integer after 1 that I find there is 2, without loss of generality. So maybe I'll find it here. Okay? So I might say something like this. So let x n sub 2 be the element of P with smallest index which is bigger than 1. And the point is in I1. You agree that one will exist. Should say x and sub 2 here. So listen to my words. Here is x1, it's in the center of some closed interval. x1 cannot be alone. It has friends from P if it's perfect. That's because it's perfect, there will be some guy in this interval, correct? And its index is n sub 2, the first one that enters this interval. So what I can do is I can take a closed interval centered at x n sub 2 that avoids x1. Take I2 to I2, which is strictly a subset of I1, such that x n sub 2 is in is contained in I2, and length of I2 is less than 1/2 or equal. So what I do is this. Oh, should be close. I'm sorry. Okay, so in general, let x n sub k be smallest, the element of smallest index of P of smallest index, such that x n sub k belongs to the interval I n sub k minus 1. Pick I sub k contained in I sub k minus 1 to be closed x n k is an element of ik, and the length of I k less than 1 over k or equal to it. Then the intersection where k starts from 1 to infinity of I k will contain some element x, and x is a limit point of P. I'm not sure if I lost you completely. I was a bit sloppy here. What's the idea? I might repeat it next class. So what's the idea here? Okay, so what you do is you pick a point x1, and then within this interval you have another point that is part of the perfect set. You take a small closed interval that isolates itself from the point x1. So what points live in this red interval? Maybe x2, x3, x4, who knows, right? But a bunch of them are deleted. Now I zoom in here. This point is not alone. I select a point and I exclude this element. Okay? And then in the intersection, what happens? If I take the intersection, I exclude it. The intersection cannot contain x1 because it was excluded after the red interval. Cannot contain x2, cannot contain x3, cannot contain x4. So this intersection will not contain any elements of P. But notice that each interval contains an element of P, so this X has to be a limit point of P, and therefore part of P, and that's the contradiction. So it was a bit sloppy. If you want to, I'll try to explain this again in next class. I just hope you get the idea. It's really a little bit annoying to write. It's a very simple idea. Why it cannot be countable.
Any perfect set in R is an interval in R.
No, there are plenty of perfect sets that are not intervals.
In R.
In R. I'll show you possibly other examples. In fact, here is a question. Can you construct a perfect set that contains no rational number? Can you construct such a set? So some perfect set that has no rational number whatsoever. Goodbye.